All right, good morning. Okay, welcome back. It's been more than a week since we had class. Do you remember what we did last time? Oh boy. Well, we're going to continue what we did last time. First, let's do a little bit of refresher of the surface integral, okay? So we're still in section 16.7. And we're still dealing with surface integrals. And we'll look at part 2 of that section today. So what we did, remember we're dealing with this kind of thing here. We're integrating some function f of x, y, z in a scalar field over some kind of surface. And we're going to parameterize that into some kind of parametric surface as a function of u and v, whatever u and v are. And then remember that this ds is equivalent to ru cross rv, the magnitude of du dv. Okay, so the steps you remember, I hope you remember, is to parameterize whatever surface you're given, find the two vectors by taking partials, cross them, take the magnitude, and integrate all over the surface. And in this case, we'll be integrating over the domain of u and v. Okay, let's do one example here. Hopefully this will bring back the memory. And we're going to do add a little bit of twist to what we have been doing. Just a little bit. Let's integrate this thing here, x squared ds. And let's say S is the lateral surface of the cone z is equal to square root of x squared plus y squared. Z is between 0 and 1. And the top circle at z is equal to 1. Okay, so the only thing different here is that up to this point, we've been dealing with just one surface. So before today, we've been dealing with just the cone, for example, just the lateral surface of the cone, and we ignore the circle at the top. Here, we're going to just add to the circle, cap it off. Okay, so we got two surfaces here. So that means we're going to be doing this thing twice. We need two surfaces, two parameterizations, do this thing twice. Let's make a rough sketch of this. Okay, so first we got a cone that we're familiar with. We're looking at just the lateral surface, the outside surface around the cone. So this one right here. And we'll call this surface S1, just on the outside. And we're going to also add to this whole thing the top circle. So we have a cone, and then we cap it off with a circle that happens at z is equal to 1. And we'll call that S2. All right, so we just parameterize the two surfaces separately, do the integral separately, and then add them together. Let's look at S1. S1 is the cone, just the outside surface of the cone, the lateral surface of the cone. And we parameterized this before. You've seen this before, and we're going to go with cylindrical coordinates. And we'll say that we'll parameterize this as R as a function of U and V, whose X component is U cosine V, Y is U sine V, and then Z, if you look at the equation here, X squared plus Y squared under root tells you that Z is equal to U. Okay, so that's just the typical cylindrical using calling R U and theta V. And the bounds on these, we know, are 0 and 1 for U, and 0 to 2 pi for V. Okay, so again, you've done this before. We've done this quite a few times, parameterizing the cone. So we shouldn't be too difficult to do that. Ru, the partial derivative, this is easy. Cosine V, sine V, 1, right? Rv, the partial derivative with respect to V, it's also pretty easy. Minus U sine V, U cosine V, and 0. Once we cross these two, we get a normal vector. And that's what we need to find the differential surface element. Crossing this, it's also very easy to do. We get minus U cosine V, minus U sine V, and U. Taking the magnitude of this, square of each one of these, add them together, put them under a root, right? After you simplify that, you should get radical 2U. All right, so I skipped a little bit of steps here and there, but it's the stuff that we have done before. Okay, so that wraps up the lateral surface of the cone. Now let's deal with the circle. S2 is the circle at the top, right? It's the circle with a z being constant 1. And you have a circle, so polar coordinate is a very good coordinate system to use. So it's cylindrical with a z held at 1, but the plane is going to be polar. So it's going to look just like this, except z will be a constant 1. And once again, u is r. It's between 0 and 1 for the entire circle of radius 1. And v is the angle. We want the whole thing, so 0 to 2 pi. Okay, then we redo all these things here. Ru cosine v, sine v, 0. Rv minus u sine v, u cosine v, 0. And when you cross them, notice that both of the k components are 0. So that's going to just give you one component in the k direction. Both the I and j will be 0 because of the last column being 0. So if you do the cross product, you should get 0, 0, u. And the magnitude of 0, 0, u, of course, is u, right? All right, so we parameterized both surfaces, the lateral surface of the cone and the cap at the top. Now we just have to do the integral. Okay, so remember, this is the integral we're dealing with. X squared ds. So we split this up into two, right? So this is going to be double integral S1, x squared ds, ds1, and then S2, the same thing. That's the lateral surface of the cone, and that's the cap at the top of the cone. All right, S1, we know what to do. We got to replace the x component of the first integral here, and the x component, looking at S1, is u cosine v. Right, so that's my x component. And ds, remember, is just the magnitude of Ru cross Rv, which is radical 2u, and then du dv, or dv du, it doesn't matter. We've gone with du dv, so u goes from 0 to 1, and v is 0 to 2 pi. Okay, so that's the first one, just the lateral surface. And now the cap at the top. Same thing. The x component of S2 is still u cosine v, so square that. And now ds2, Ru cross Rv for the second surface is u, and then du dv. Okay, so you split this up and then you parameterize them, Ru cross Rv for each one of them, integrate. Okay, the integration left here is not difficult at all. So we're going to skip the details there. And we'll end up getting this thing here. Okay, the actual integration is very, very straightforward. You do need to use the trig identity for cosine square at some point, but that's not challenging. Okay, so that's how you handle these multiple surfaces. If you have, say, like a cube, for example, then you would have 6 surfaces. Then you divide them into 6, the same way we did here, and then do Ru cross Rv for each one of them. Questions? Does that bring back the memory of what we did last time? Yeah? All right, now things are about to get really interesting. We wrapped up the scalar field one. We're going to do a vector field integration now. So that wraps up scalar field. Surface integral. Now we're going to do a surface integral over a vector field. Okay? Now before we can do that, we have to talk about the orientation of a surface. Now this is a strange concept here. With the line integral, we know the orientation. As t goes on, which way this thing points, that's the orientation of a line integral. Now with a surface, there's really not a direction to that. But if you think about it, there is some kind of direction involved. Because for every surface, there are 2 normal vectors. You can do Ru cross Rv or Rv cross Ru. They're in the opposite directions, but there are 2 of them. Okay? So given this parameterization, whatever parameterization we end up getting, both RU cross RV and RV cross RU are vectors normal to the surface. And the only thing different between these two is the direction. These two are pointing in the exact opposite directions. One is the negative of the other, right? That's the only thing different between these two. So imagine you got a surface looking like this. This first vector, this might be RU cross RV, for example. And of course, the one that's pointing the opposite direction is going to be the reverse of the cross product, which of course is just the negative of the other one, right? We know that. So when we do a scalar field integration, we know that the differential surface element is this thing. The magnitude of RU cross RV, which of course is the same as the magnitude of RV cross RU. Right? So it didn't matter which way we crossed when we did a scalar integration. When we do a vector integration, now we got to be really careful which one we're using. And we have to agree before we do the integration which one we choose to use, either the one pointing, let's say in this example, up, or the one pointing down. So in vector field integral, we need to decide which normal vector to use. And that gives the surface an orientation. We can say it's oriented with a normal vector pointing up, or it's oriented such that a normal vector is pointing down. You have to just pick one and stick with it. Usually, but not always, for a closed surface, like a sphere, for example, we use the normal vector that points outward. Usually. Okay, so imagine a sphere here. There's two choices of any normal vector. We can have one that points out like that, or we can have one that points in, right, into the sphere or out of the sphere. Normally we choose the outward one, but not always the case, and you have to read what the statement says, which one to choose. Okay, now we know what it means to have an oriented surface. Now let's talk about what it means to integrate over a vector field. The surface integral of a vector field is often called a flux integral. Physically, you can think of it as measuring the amount of stuff flowing through that surface. More specifically, the rate, the flow rate, the rate at which stuff is flowing through that surface. So if you imagine you have a surface that doesn't change the flow and you put it in a river or something, and you want to know an hour later how much water has flown through that surface. That's what the flux integral can tell you. Okay, so let's see. I'll give you a physical description of what we're doing here. So here's some kind of surface. And these green arrows, these are the vectors in my vector field. I'll have them all go in the same direction for simplicity, but they don't have to. Vectors in vector field. Okay, now let's pick one of these points on the surface here. And let's take right here. Now I'm going to draw the vector that's normal to the surface. So that's my normal vector. This is my vector field vector. So the red vector indicates a unit normal vector at that point where we have a green vector field in the vector in the vector field. So what we want to do here we want to know the flow rate of stuff through the surface. Okay, so I got surface right here. It doesn't change the flow. And imagine these green arrows indicate the flow of water, of whatever, right? We want to know that this surface sitting in this fluid here, over time, how much of things are going through that surface. And of course, we only care about the parts that's actually going straight through the surface. Any part that's parallel to the surface is not going through it. We don't care about it. So only the component of F, perpendicular or normal to the surface, matters. Any component that's parallel to the surface just slides right off. If it's water, they just slides right off. It doesn't go through the surface. We want to know all of these components going through in the normal direction. So we want to know how big of a component of F is in this direction. And that involves a dot product, right? When you do a projection, we use a dot product. All right, so let's just take those two vectors there. So here's F. And here's my unit normal N. The component of F in the direction of N is, remember how to find that? How do you find the component of F in the direction of N? You got two vectors. You want to know how much of this green vector is in the direction of N. The red one, what do? It's a projection. So how do you do a projection? How about a dot product? Does that sound good? Yeah? Yep, that's how you do that. Right, if you take the dot product of these two things, then you end up getting the component of F that's in the normal direction. Okay? Now at this point right here, we still have our usual RU cross RV and all that stuff. Right? And then, of course, RU and RV, if you cross them, take the magnitude, you get a little patch of that surface. Let me make this U here and that V. So RU cross RV gives me N. Okay? So this means that the amount of stuff through the small patch is F dot N ds. Right? ds gives me the area of that little patch. We imagine that over this small area, the amount going through is just F dot N. So F dot N, that's a scalar now, scalar ds. That gives me the amount of things going through that little surface in the normal direction. To accumulate over the entire surface, we just do an integral over the surface. Right? So that's what we do. F dot N ds. Physically, just think F dot N as the amount of fluid going through the surface perpendicularly, and ds is a little patch, small patch of the area. Integrate over the whole thing. Now you know over time how much of that is going through the surface. This is often written as this way, in a more compact notation. Sometimes you see this written as F dot ds, big S with an arrow over that. Even though the surface is not a vector, because we're orienting that surface in some way, we treat it kind of like a vector. It has an orientation, so we give it a vector kind of like direction. And of course, ds is just a shorthand for n ds, no vector. Okay? Now we're going to have to worry about how to calculate this stuff. See, I told you things are about to get interesting. So how do we actually calculate that? Remember that n is the unit normal. So that means that this n vector, to get a normal vector, you do Ru cross Rv. And to make it a unit vector, you divide it by the magnitude, right? Or Rv cross Ru divided by its magnitude. And this depends on which normal vector we use. And the problem will tell you which one to use. So you got to be careful you use the right one, either Ru cross Rv or Rv cross Ru. And of course, the difference between the two is just a sign, right? So we have to be careful which one we use. But let's assume that we use the first one, okay? We already know that ds, the ds we use in scalar field calculation, is simply the magnitude of Ru cross Rv du dv. So if I take this normal vector into here and the ds into here, I can simplify a little bit. F is whatever the vector field is, dotted with n. Right? So that's my n vector. And then ds from here, du dv. And so what's nice about this is that you don't have to worry about the magnitude anymore. These will cancel. So we end up doing just simply the integral of f dotted with Ru cross Rv du dv. And of course, you got to be careful which normal vector to use, right? There are two of them. You have to be very careful, read the problem carefully and find out which one you're using, and then use the correct one. All right, so that took a little bit of time to get to this point, but this is how we calculate a surface integral in a vector field, the flux integral. And this physically, keep in mind, measures how much of that stuff is flowing through the surface. So you might remember a few years back, one of those giant oil rigs had a leak at the bottom of the ocean, right? Now people were trying to figure out how much crude oil was being pumped into the ocean at any given time. And it was very difficult to do. But there were ways to estimate that. And one way was to take a picture of the crude oil coming out of the bottom of the ocean and do a surface integral of that little area there and try to get some kind of estimate of how much was coming out. That would give us some kind of a ballpark guess. Wouldn't be very accurate, but at least some kind of ballpark guess of how much crude oil was being pumped into the ocean. And the answer turned out to be a lot. A lot. All right, let's do an example. Let's do this integral here. Let's say our vector field is zi plus yj plus xk. And our S surface can be parameterized this way. U going between 0 and 1, and V is between 0 and pi. And now we have to define how we orient our surface. In this problem, we're going to define our surface as being oriented upward, an upward orientation. Now what this means is that we want N to have positive K component. Right? That's what it means to have an upward orientation. So that means when we do our surface integral, we have to make sure that RU cross RV has a positive K component. If it doesn't, then we switch it around, right? So that's what it means to be. This tells us which vector we're going to be using. Okay, and this is a pretty simple case right here. We got our surface already parameterized. There's nothing more to do. We just go ahead and proceed with RU, RV, and do the cross product, right? All right, so RU, this is simple. Cosine V, sine V, 0. And then RV is minus U sine V, U cosine V, and 1. Now normal, we can do either RU cross RV or RV cross RU. Whichever is oriented correctly. In this example, we want it to be oriented upward. That means positive Z. Okay, you always have two choices once you do RU and once you find RU and RV. You always have two ways to cross these things. The problem will tell you which normal vector you want, and that's the one you want to use. And of course, just by looking at them, you don't know which one's going to give you the right one. Just go ahead and cross them any way you want and adjust the direction as needed. All right, so I'm going to do RU and cross RV here. And when I do that, this cross with that, I get sine V minus cosine V and positive U. Okay? is that vector pointing upward? Does it have a positive k component? Yeah, right? This is u, and u is between 0 and 1, right? So yes. 1 second. Yes? Then that meant I used the wrong order. I just flipped around. So if I have a negative u here, that means I should have been doing RV cross RU. So let me write that down. Good question. If wrong direction, reverse cross product order. Okay? Oh, yeah. In that case, then you're going to have to break it up, kind of like what we did with the cone. And that's a very complicated. We don't want to worry about that just yet. Okay, let's get this the simpler stuff first. But in that case, what we would do is kind of like the two surface thing. Now, if you flip the direction, flip the order of the cross product, then you just basically change the sign of everything. So you're just crossing any order you want, and then if it's the right one, you proceed. If not, you flip it. Okay? Now we got what we need. We can do our surface integral. Remember, at the end of the page I just took away, this ends up being a double integral of f dotted with RU cross RV du dv. And we integrate as usual over the domain of u and v. All right, for us here, remember f. F in our case, the vector field we got is zi, yj, and xk. And the surface that we're using, that we're given, r cosine v, u cosine v, sorry, u sine v, and then v. Okay, so f. First f, z is v, right? Z is v on the surface. V, y is u sine v on that surface. And then x is u cosine v on that surface. So this is f. And then we're going to dot this with our u cross rv, which we found on the last page, sine v minus cosine v u. And then du dv, or dv du. It doesn't really matter. They're both bounded by constants. So let's do du dv. So this will be 0, 1, and then 0, I think pi in our case. Right? Okay, then you start them. 0 pi, 0, 1, v sine v, minus u sine v cosine v, u sine v cosine v, and then u squared cosine v, du dv. The first round of integration is with respect to u. U goes from 0 to 1, so that's actually pretty easy to do. The first round is very easy to do. This guy doesn't have any u, so he gains a u. Here we already have a u, so that's minus u squared over 2 sine v cosine v, and then u cubed over 3 cosine v. And then you'd get evaluate 0 and 1 for u. All right, so you can see the first round of integration is very, very easy. It's the next round that's a little bit annoying. So this is just going to be simply v sine v minus 1/2 sine v cosine v plus 1/3 cosine v dv. All right? How do you integrate v sine v dv? Parts, right? And when you do by parts, normally we use u and v. You want to stay away from v because v is already used. So use something else. How do you integrate the middle part here? Substitution, yeah. How about this guy? That's easy. Direct integration of cosine, right? So that's how you do end up getting this. Now, that's going to be a little bit of work, especially in the by parts part, but it's not terribly difficult. This ends up being just pi. All right, I think we've had enough for today. So let's end it there, okay? I'll see you again Wednesday. Well, what do you think?
Well, it's
Some
x
kind of
and y is
circle,
going to be
right?
a circle,
Right.
and I was confused by the z component going from 0 to pi. Would it be like a snow cone kind of deal, or?
This would be a like a like when you go into a cathedral, you have this kind of spiral staircase kind of thing. It's like a helix, except it's not just a line, but it's a pull out a picture. It's called a helicoid, I think is what it's called. Yeah, it's one of these guys.
Now, how does that work then? Because the z component
The
goes
z
from
component
0
goes
to
0 to
pi.
pi, yeah.
How do you?
So it starts at 0,
Mm-hmm.
goes up to pi.
Oh, just the pi. Oh.
Pi is just a number, right?
Okay.
They go from the 0 ground
Oh,
floor to
okay.
pi 0.
So,
That is what it looks like. It's a
really? Okay.
helicoid. Yeah, that's what it's called, helicoid.
Cool. Yeah, I was.
It's like a helix, and remember you add the word coid to it, you make some kind of surface, right? Coid, paraboloid, that kind of thing. So it's a helix, oid,
Okay.
helicoid.
Awesome.
So it's a
Thanks.
spiral staircase, like I said.
Hi. I don't think we went over the
usually.